Okay, so the next section of homework is logarithmic equations. So, logarithmic and exponential equations are kind of they are inverses of each other if they have the same base. And so you can represent the relationship between three numbers either logarithmically or exponentially. So the first problem, they're asking us to rewrite this in the equivalent exponential form. So the base is always this number, the subscript. So it's going to be 3. And the number we raise it to is the fourth power. And the answer is 81. So you can always check these out, especially if they are whole numbers, because 3 times 3 times 3 times 3 is 81. 3 times 3 is 9. 3 times 3, so 9 times 9 is 81. So that's the equivalent exponential equation. So again, here the base is 10. The exponent is -3. The result is 1,000th. And that makes sense because when you have a negative exponent, you can take the reciprocal of that. So 10 to the -3 power is the same as 1 over 10 to the third power. And 10 to the third power is 10 times 10 times 10, which is 1,000. Okay, number 3. The base is 16. The exponent is the 3/4 power. The answer is 8. How about this one? Well, what it's saying here is we're taking the fourth root of 16 cubed. So another way you can think about that is it's the fourth root of 16, the whole thing cubed. Is that right? No, that's not right. How do we want to think about that? Well, it is true. Maybe that is true. Another way to think of it is you can you can do whichever one you do first. You can cube it and then take the fourth root, or you can take the fourth root and then cube it. So this is also equal to the fourth root of 16, the whole thing cubed. And the fourth root of 16 is 2. That's because 2 times 2 times 2 times 2 is 4. So you get 2 cubed, which is 8. Okay, so that's doing that. You can also go the other direction. You can write the logarithm. So the base is going to be 81. So it's going to be log to the base 81. The result is the exponent, and this is the second number on the right hand side is that. I think that's right. So they're asking what number do I need to raise 81 to get 3? So it's saying 81 to the fourth power. Yeah. So if you think about how logarithms are defined, logarithm means what number do I need to raise the base to get this result. And so how do we know this original thing is true? So the fourth power, the fourth root means you take the fourth power means you take the fourth root. And so what number multiplied together 4 times gives you 81? Well, the answer is 3. So the fourth root of 81 is 3. So it's the number multiplied by itself 4 times gives you the answer inside there. Okay, the next one, again, 6 is the base, so it's log of base 6, and the result is the argument of the log is the answer on the right-hand side, and the right-hand side is the exponent. What number do I need to raise 6 to get 1/36? And that's true, because if you think about this, is 6 to the minus 2 power is the same as 1 over 6 squared. And 6 squared is just 6 times 6, so you get 1/36. Okay. Here we have a base of e, so that's the natural log. You know, you could say log to the base e, or you can just say it's the natural log. This is what you put inside. So it says the natural log of 1.6487 is a half, and you can do that by sticking your calculator, because your calculator has the natural logarithms. So if I do the natural log of 1.6487, I'll get 0.4999999. So, and what it's saying, again, what number do I need to raise e to get this number? Well, I need to raise e to the 1/2 power to do that. Okay, next one says, evaluate the function at the indicated value of x without using a calculator. So it's saying, you know, what is f of x when x equals 1? So what you do is you just plug 1 in there and see if you can figure it out. So log to the base 7 of 1. So the question is, what do I need to raise 7 to get 1? Question mark. That's the answer. Well, any number raised to the 0 power is 1. So this is going to be 0. So anytime the argument of the logarithm is 1, the answer is 0. So I could say log to the base 100 of 1 is 0. I could say log to the base a of 1 is 0. So no matter what the base is, if you have 1 as the argument, you're going to get 0. Okay, so that's how that works out. The second one, if you stick in x equals a squared, you get log to the base a of x squared. So now the question is, what is, oh no, that's not right. You put in a squared. So this is basically, and the answer is something here. So I know what the answer is. I just want to make sure I'm not using something you don't know at this point. So you can, the base is a, and the question is, what is the exponent? So you get a squared. Well, the answer is 2. So you kind of have to think of it in the exponential version. What do I need to raise a to get this result? Well, a to something, when you already know what the exponent is the same thing. Okay, now we're going to match some graphs up. So I must have to delete this page because there must be some pictures of graphs. Okay, so there we have. We have lots of little graphs now. We have 8 of them, 6 of them. And these are all log base 3. So let's plot the parent function on one of these here. So the log of, so we just look at, well, here, do we have just the parent function? No, let's do that. Log base 3 of x. So if you let x equal 0, you can't that can't happen. Okay, so if you let x equal 1, we just talked about that. The log to the base anything of 1 is equal to 0. The next thing is the log to the base 3 of 3 is 1. Anytime you have the same base, the argument is the base. It's saying, what do I need to raise 3 to? What power do I need to raise 3 to get 3? Well, it's always the first power. So let's plot those two. So you're going to have 1, 0, and you'll have 3, 1, And likewise, if you go 1/3, here we went 3, 1. If we go -1 in this direction, we'll have 1/3. It's kind of the reciprocal. So this is my parent function, something like that. So let's think about what's going on here. Notice this line is shifted by 1 unit. Everything's been shifted by 1 unit. So this must be just the parent function with a x-axis shift of 1 unit in the x direction. So this one looks like the right one. So this is going to be 12 because it's the parent function shifted to the right by 1 unit. Okay, let's look at the next one. Now this one is flipped around the y-axis. So this goes this way. It's flipped. If it was flipped, it would go through there, but it's shifted over 1 unit to the left. So let's just write this out. Just think about what's happening. So you're going to have log to the base 3. Since it's shifted across the x-axis, you have the negative sign, and then you have the translation inside the parentheses, and it's translated -1, so we're going to add 1 here. So we might see this form of the equation, or we might see -x minus 1. Do we see either one of those? This is the one that looks most like it, except it's shifted. Oh, another thing that's happened is this thing has moved down, I think. We've actually, no, actually, what have we done? We've shifted 1 unit in the x positive direction. Yeah, so you can see this. Think about this vertical asymptote. I've shifted the vertical asymptote of over 1, and then I flipped it. So that's what the problem is. It's really going the other direction. It's that. And so this one, if we multiply it out, we'll get 1 minus x. So that looks like that one. So this must be 13. Okay. Now this one looks like it's been flipped around the x-axis and the y-axis because it's going down and it's going to the left. So this should have 2 negatives. And let's see what's going on. This point started here. Let's think about this. What's going on? Here's 1 unit over this way. So let's see what happens. So let's just draw the parent function and then go through each one of these. So there's that way. Now if you flip it over the x-axis, it's going to look like this. Go through there, and then it looks like it's been flipped around the y-axis. So it's both of them. So what we're looking for is where you've got a negative out front and you've got a negative inside, which looks like that one. So I would go with 14 on that one. Now here it's only flipped around the x-axis. So that's this one here, 10. So that's 10. Now here we've got, it's shifted 2 units in the x direction because here's the vertical asymptote. And it has, here's x equals 1. Normally it would be over here for the parent function. So if I just flip this thing around, yeah, but it's not going this way, so we haven't flipped around the y-axis. We've flipped it around the x-axis because it's going up like this instead of down. So this is, if we just flipped it across the x-axis, it would look something like this, kind of like that, but it's been shifted 2 units in the direction left in the direction. So this is going to have, this one's going to have because it flipped across the x-axis, it's going to be a negative sign out there. You're going to have log to the base 3 of x, and it's positive x because we haven't shifted it across the y-axis, we shifted it across the x-axis, reflected it, and then it's moved 2 units in the left direction, so we're going to add 2 to that. So there we go, that's that one. So that's 11. And then this one looks like it's normal, except instead of crossing through the x-axis here, it's been shifted up 2 units. So this one should look like the normal parent function, log to the base 3 of x plus 2, which is 9. So we didn't have any repeats, so that sounds... And I would suggest you just go back and make sure you can convince yourself that you know what the heck I'm talking about here. Okay, so the next bunch of problems are going to be finding the domain, the x-intercept, and the vertical asymptote of the logarithmic function and sketch its graph. So we'd learn a different way in section 3, but right now we're in section 2. So in each one of these cases, we're going to create a table of x versus y. And so let's do that. So let's make it about this big. So we'll need an x column. What we'll do next is just the logarithm part, and then we'll have an extra column just in case we want to make some comments here. So the first column is x, and then we have log, in this case base 3 of x, and then negative log base 3 of x plus 2. Now the, the values for x, we don't want to pick 1, 2, 3, 4, 5 like that. Basically, you're going to have 1, and then you're going to go either side of it, depending upon the base. So I've got a base of 3. So what you do is you do powers of 3. So 3 to the first power is 3, 3 to the second power is 9, and you go the other way, 1 over 3 to the first power, and 1 over 9 to the first power. And what we have here is we have 3 to the 0, 3 to the 1, 3 to the second power. Here we have 3 to the minus 1, 3 to the minus 2. So in terms of exponential notation, that's going to be, you know, what value do I have to raise 3 to get x? So if I have x equals 1, log base 3 of x, well, I need to raise 3 to the 0 power. So let's start with 1 here in the middle. So when x equals 1, log base 3 of x is 0. These are the exponents. So the log base 3 of the thing is the exponent to give me these x values. So I have 1/9, 1/3, 3, 9. So the log base 3 of 1/3 is -1. That's because 3 to the -1 power equals 1/3. This is -2. This is +1, +2. And then I could just take the negative of that and add to 2. So the negative of -2 is +2, and then add 2, I'll get 4. The negative of -1 is +1, and add that to 2, I'll get 3. And you can see now once I get started, I can just fill those in. So now to plot that, I need some graph paper. Need some graph paper. Wake up! Okay, there it is. Not sure why that did that. Okay, so what we'll do is for x equals a ninth, so let's, we'll still go from negative 10 to positive 10, negative 10 to positive 10. So when x equals a ninth, that's going to be really close here. And you get 4. 1, 2, 3, 4. And then for x equals a third, which is about right here, you get 3. So that goes right there. For x equals 1, you get 2. So that goes there. For x equals 3, 1, 2, 3, you get 1. For x equals 9, you get 0. And then you can kind of draw a line through these things. Okay, what we've done here really is we've taken the logarithm function. Log base 3 would be x equals 1, y equals 0. You get x equals 3, y equals 1, x equals 9, y equals 2. You'd have this function right here. So from a transformation standpoint, what we're doing is we're flipping it across the x-axis. So we're, instead of going this way, we're going to go that way. And then we're shifting it in the vertical direction 2 units. So you can see 1, 2 vertical units. Okay, so now to answer our questions here. The domain, so if you look at the graph, you can see the domain is x has to be greater than 0. So let's put that over here, domain x has to be greater than 0. Not just greater than or equal to 0, but just greater than 0. The x-intercept, well, that's going to be x equals 9 or 9 comma 0. Again, you can see that on the graph here at 9 comma 0. And then the vertical asymptote, well, the vertical asymptote always corresponds to where the domain starts. So an asymptote is an equation. So x equals 0, since we go from just greater than 0. So the vertical asymptote is where you approach. And in this case, if you look at the graph again, we're going to approach positive infinity here for the y-axis, which is x equals 0. Okay, 16. So here we got f of x equals negative log base 6 of x plus 2. So let's do the same thing. We're going to make it about this big. Now, if you remember, the log base anything of 1 is going to be 0. So what we'll do is we'll choose, instead of choosing here on the previous problem, we let x equals 1 be the case where the log base 3 of x was 0. So if we do the same kind of thing here, what we're looking for is some kind of middle value. And to get an argument of 1 in here, I don't put in 0, because if I don't put in 1. If I put in 1, I'll get 1 plus 2 is 3. So to get a result of 1, x has to be negative 1. So I'm going to use negative 1 here. And then what we'll do is so it's log base 6. So if you remember over here, we went from 1 to 3. So we went, so we're going to do the same thing here. If we went from 1 to 6, that would be 5 units. So we need to go 5 units further in this direction. So you'll see that if I add 5 to this, I'll get if I add 6 to this, I'll get, is that right? So actually I added 2. 1 plus 2 is 3. So what I'm going to do is I'm going to take this number and add not 3, but not 6. I'm going to add 1 less than that. So if I add 4, 1 less than 6 is 5. So if I add 5 to negative 1, I'll get positive 4. And likewise, what I'll do is I go back here, I had 1/3, so I need the same kind of ratio, except here I went back from 1 to 1/3. If I went a whole unit in the negative direction, I would get 0, or negative 2. So what I really need is negative 1, and what am I going to put in here? I'm going to put in negative 1 and 5, 6. Okay, so let's just humor me for here a second. So what I do is the argument is going to be x plus 2. So if I add 2 to this, I'll get 1. If I add 2 to this, I'll get 6. And if I add 2 to this, I should get 1/6. So that's the whole idea. Now to go to the next step, I'd have to add, here I added 8, because 1 plus 1, 9 minus 1 is 8. So here I'd have 6 squared, which would be 36. So it would be 36, and it'd subtract a negative 1, so it would be 36 minus, let's just try this out and see if it works. So if I take x plus 2 here, I get 34 plus 2, which is 36. Okay, so that was right. So then when I take the negative log base 6 of x plus 2, I'm going to take the log to the base 6 of this result. And so that is going to be minus 1, this is going to be 0, this is going to be 1, this is going to be 2, just like I had over here. So I have to kind of adjust the x values to make everything work out. And if I did this, it would be negative 1, and I'd have 35, 36. Because if you square 6, you get 36. So I need 1/6. And if I add 2 to this, I'll get 1 over 36. And that's going to be negative 2. Okay, so let's add a page. Get a piece of graph paper. So if we plot those points, we get, what we're going to have is, we can't have any number less than negative 2, because then we'd get a negative argument in here, which is what we can't have. So we're going to draw a vertical asymptote here at x equals negative 2. It just helps us also figure what's going on here. So negative 1 and 35, 36, that's going to be really close to the red line, and the value is going to be equal to negative 2. So that goes, is that right? Yeah, actually these should be opposite in sign, because I'm taking log to the base 6 of this, which is negative 2, and then I take the negative, so it's going to be plus. So these will be plus 2, this will be plus 1, this will be minus 1, minus 2. Okay, now we can plot them. So we go over 1 and 35, 36 plus 2. That puts us really close to there. Then we go 1 and 5, 6, which is really close to here, and that's plus 1. That. Then we go negative 1x, 0y, so that's that point. Then we go 4, 1, 2, 3, 4, negative 1, and 34, of course, that's way out here, so we really can't draw that in there. So we draw this vertical asymptote coming down here through these 2 points, go like that, and then we have to kind of just show that it's not going too quickly. So again, from a transformation standpoint, what we've done is we've moved everything in the x direction 2 units to the left. Remember, it's x minus h. So h is -2. So we move it to -2, and then we flip it around the x-axis. So if I just did this, it would look like that. And because of the negative sign, though, it gets reflected across the x-axis. So to answer the questions again, the domain. So from the graph, we can say the domain is x has to be greater than -2. The x-intercept, so that's what crosses at x equals -1, so the coordinate is -1, 0, and the vertical asymptote is a vertical line at x equals -2. So again, the domain, the vertical asymptote is at the edges of the domain of this. This red line here is x equals -2. Okay, next one. So here we got x divided by 5. So again, we're going to make this table up about the same size. If I make it a little too big, no big deal. So again, I'm going to pick the x values to make this thing work out. So this is x, and this is x over 5. And then we'll do log to base 10 of x over 5. And what we want is this to be 1. And, is that right? Now what we want, yeah, x over 5 is 1. The log of 1 is 0. So that's going to be, so we take the log to the base 10, or any base of 1 is 0. So that one's 0. To get, if this is 1, then x has to be 5, since x divided by 5 is 1. Okay, so and then we're going to go to yeah, what are we doing here? So what we're going to do is we're going to go this way towards 0, and we're going to make it so that we want to have, what we want is 1/10 here. So we take the reciprocal of 1 over 10, and then we'd have 1 over 100 here, and here we'd have 10, and here we'd have 100. So those would be the values of x over 5. Hence, if we take these and multiply by 5, we'll get 5/10, which is a half, and here we'll multiply by 5 to get 5/100. And here we take 5 times 10, which would be 50, and then 5 times, that'd be 500. Okay, so then when we take the log here, the log of x over 5 is -1, x over so the log to the base of 1/100th is going to be -2, and this is going to be +1, this is going to be +2. Okay, you can kind of see how all these are happening. These, I'm trying to get ±1 and ±2 and 0 as my y values. You kind of have to work your way backwards. Normally you do this, go this way and go that way, but we're really trying to work from this way and go the other direction. So now if I wanted to plot this, now I probably would want to change the scale because I want to run out of room pretty quickly. From the x value perspective, I could leave it the way it was, -10 to +10. In the y direction, that's wrong. In the y direction, I can leave it the same. In the x direction, I have to kind of build in what's going on. So I go from 5/100 to 5/100 to 500. So I probably say this is 500. This is -500. This is +10. This is -10. So I'm going to plot x versus y. So 5/100 and -2, so that comes down here. It's really close to the y-axis. Here I have a half, except that's not a half. So if you remember the scale here, this is going to be 50. How much? 50, 100, 150, 200. Yeah. So this is 50. This is 100, 150. Let me just put in. So this would be 100. This would be 200. This would be 300. 400. So this first one you can't even hardly see. It's just so close. Even this one's really close. Then we have at x equals 5, which is still really close. If this is 50, then 5 would be about right there. And then we have 50, which would be here, and that would be 1, positive 1. And then 500. So you go 500 and positive 2. So this thing would just really close to the x-axis, and then it would go like this. So as far as the x-intercepts, well, the x-intercepts when y equals 0, so we could say the x-intercept is x equal to 5 or 5, 0. The domain, I forgot the domain, you can see that x has to be greater than 0 because you can see how it approaches. It gets really small but never negative. And then the vertical asymptote is x equals 0. So that's, one of the difficult things about logarithms is you've got to kind of think in a backward direction. It takes a little while to do that. Okay, so here we have the natural log. So the natural log is log to the base 2.7818. And you have x minus 2. So again, we're going to make up our table like this. And what we want, the result here, the natural log of x minus 2, we want to be -2, -1, 0, 1, 2. So let's, so x minus 2, and then we want x. So ultimately we want to plot x versus f of x, which is the natural log of x minus 2. So to get, if you take the natural log of 1, you get 0. The log of any base of 1 is 0. Then what you do, you want x minus 2 here to be equal to 1 over 2.718. Here you want it equal to 2.718. Here you want it equal to 2.718 squared. I said 2.7818, so let me see what E is. I've already forgotten. That's pathetic. Okay, so E is 2.718 m. 2.718. So this will be 2.718 squared, which is 7.4 approximately. Here you'd have 1 over 2.718 squared. Let me just erase this thing in here. So you have 1 over 2.718. So 1 divided by 2.718 is 0.37. And here you need 1 divided by, oh, that was, yeah, 2.718 squared. That's going to be equal to 0.14. And now we can, to get here, we have to add 2, 2.14, 2.37, 3, 4.718 and 9.4. Let's see if I did that right. Okay, so let's go in the opposite direction, see if this works. 3 minus 2 is 1. The natural log of 1 is 0. 4.718 minus 2 is 2.718. The natural log of 2.718 is 1, because that's e. That's the base. Here I subtract 2 to get 7.4, which is e squared, and therefore the log of this number squared is 2. Okay, so I've convinced myself that I did that right. So now we can plot this with our 3 values of x, or 5 values of x. So we have 2, let's use, since we go up to 7.4, we can, actually we go up to 9.4. So we're going to have 10 here, negative 10 here, go up to plus 10 here, minus 10 here. Okay, so the first one is 2.14 and negative 2, so that goes right there. 2.37, which is a little bit to the right. Negative 1, 3, 0, 4.7, so that's 3, 4, 4.7, and I get 1, 3, 4, 4.7, 1, and 9.4, which is about right there, 2. And you can see I have this vertical asymptote at x equals 2, like that. So that's my vertical asymptote. Then I'm going to approach this vertical asymptote from down here. I'm going to go up through these 3 points, through the x-axis, and then I start to loop off here in that direction. So back to our question. The domain is x is greater than 2. The x-intercept is x equals 3, so that's this one here. You see it over here. And the vertical asymptote that's a line which is x equals 2. Again, these kind of complement each other. So you can see this is the line x equals 2. From a transformation standpoint, you could plot the logarithm of x, the natural log of x, which would have x equals 0 as the vertical asymptote. And then all we're doing is shifting everything to the right 2 units. Okay, so that's how those work out. And then the last, well, no, not the last, so we got a couple more here. So it says plot the following function. So you're going to do the same kind of thing. They're just not asking. In the last one, they didn't ask us to plot it, but I plotted it just because I thought it was worthwhile. You could have gotten the answers from just the tables. So we'll do a table as well here. Well, there's 2 ways you could do these. You could plot the parent function and then do the transformation, or you could come up with a table. So let's do both ways. So here's my table. Again, we want the result here, log base 10 of x minus 1 to be equal to 0, negative 1, negative 2, 1, 2. And here we have x minus 1, here we have x. So the logarithm of 1 is 0. Because the base is 10, what we do here is 1/10, then we do 1/100th, and then we go to 10 and to 100. So 10 squared is 100, 10 to the first power is 10, 10 to the 0 power is 1, 10 to the negative 1 power is 1/10, 10 to the negative 2 power is 1/100th. And then to get here, what we're going to do is we're going to add 1. So this will be 1 and 1/100th. This will be 1 and 1/10th. This will be 2. This will be 11. And this will be 101. So with those, you can see what the x-intercept is. It's x equals 2 is the x-intercept. You're going to see a vertical asymptote here at 1 because we're approaching 1, but we're never equaling that. So we could use those things instead of plotting them. We could almost, actually I don't want to do that because I've already got a piece of scrap paper. So let's, or did I have a piece of scrap paper? Yeah, there it is. So 1 and 1/100th, so that's just to the right of this. So let's draw a vertical, let's go ahead and draw a vertical asymptote here at 1. So at -2, y, we have an x of almost right there. Then at y equals -1, we have a 10th, which is going to be right like that. At 2, we have 0. At 11, which is just off the sheet here, we have 1. So I didn't plot this point because it's way off. So you're gonna come like this, go through there, and then loop down, and then approach this vertical asymptote. So that's how you do it plotting wise. You could plot the parent function, which in that case the parent function would be log to the base 10 of x instead of log to the base 10 of x minus 1. So everything would just be shifted over. So to get y equals -2, you'd have 100th. For y equals -1, you have a 10th. It would go through here, and then you would go to 10 for the next one, and so that would be your parent function, and your actual function would just be shifted over 1 unit in the x direction, because you have the argument is x minus 1, x minus h, so h is 1, so you move everything, translate to the right. So this one's going to be similar, except it's not going to be quite so stretched in the x direction. So we're going to have this, again, the table, and we want the result. So we want the result here, the natural log of x plus 2, 0, -1, -2, 1, 0. So what we have is x plus 2 here. So the argument to get -2 as the result, you have to have 1 over e squared. Here you have to have 1 over e. Here you just have to have 1. Then you have e, and then you have e squared. So we just need to figure out what those are. Plug those in our calculator. Third one, I think I can do that one. This is 2.718. 2.718 squared. 718 squared is like 9 or something like that. No, it's not quite 9. 7.38. 7.39. This is 1 over this. So if you take 1 divided by 2.718, you get 0.368. And then 1 divided by 7.39 is 0.135. And then so my x values, I'm going to subtract 2, because I add 2 here, so I'm going to subtract 2. So I'll get, if I take 0.135 and subtract 2, I'll get -1.865. If I take 0.368 minus 2, I'll get -1.632. Here, if I take 1 and subtract 2, I'll get -1. Subtract 2 here, you get 0.718. And subtract there, you'll get 5.39. So what I'm doing is I'm plotting these two results. This is an intermediate thing to help me guide me in the correct process. So let's think about the vertical asymptote. Well, you can see as the y value gets more negative, this is going to approach -2. So I'm going to draw a vertical line at -2. That kind of helps set things up. And then I'll plot these. So -1.865, that's about here, and you get -2, so that's here. Let's put the scales. So let's just be the normal scale that we have for the x and y axis. Okay, next one, -1.6. So there's -1.5, -1.6, -1. So that goes there. -1, 0. So that's my x-intercept. 0.72. So I go over here. Here's 1. Here's 0. 0.72 is about there. Go +1. And 5.39. So 1, 2, 3, 4, 5. 3.39 is 2. And those are my points. And so this is going to approach this asymptote. Comes up here, goes through these 2 points through y equals 0, through there, and then like that. And again, I could draw the parent function. The parent function would be the natural log of x. And that would have x equals 0 as the vertical asymptote. At -2, y, I would have 0.135. At -1, y, I'd have 0.368, should be right there. At 1, I'd have, so here you'd have 1, 0. Here you'd have 2.718, so 1, 2, 7, 8 there, and then you'd have 7.39, 1, 2, 3, 4, 5, 6, 7.39, 2. So that would be my parent function, and all I'm doing here with this natural log of x plus 2, it's x minus h, so h is -2. So, oh yeah, so that's what I did, is I took this and I moved everything -2 units. And if I measured these distances, if I did this accurately, these all would shift 2 units. Looks like it's less here, but in the x, that's true in the y direction, but in the x direction, you should have the same shift of 2 units to the left. Now the last one is a little more difficult because you've got this factor of 3, which is that's going to stretch it in the y direction, and this is going to move it in the y direction. So as far as the table is concerned, it's actually pretty easy. It's easier than the other ones to figure out what to do. Because if we just let x equal negative, well, what is it? So it's log base 2. So the x values are going to be 1. The log base 2 of 1 is 0. So the log base 2 of x. So log base 2 of 1 is 0. And then we do 1/2, which is 1 over 2. And we do 1 over 2 squared, which is 1/4. Here we have 2, and here we have 4. So you can see I have 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the -1 power, 2 to the -2 power. So when you do the logarithms, you get those numbers, which are the exponents. And then the last thing is I can do 3 log base 2 of x minus 1. So I'll take this times 3, which is -6, and subtract 1, which is -7. Here I'll take -1 times 3, which is -3, subtract 1, that'll be -4. 0 times 3 is 0, minus 1 is -1. Then I have 3 times 1, which is 3 minus 1, which is 2, and 3 times 2, which is 6. 6 minus 1 is 5. And you can see everything's shifted by 5 units. Is that right? No, actually it's not. It's variable because of this multiplying factor. But I can plot that on my graph easily. kind of like learning to, if you're a right-handed person trying to learn how to do things left-handedly, or if you're driving in a country where they're driving their left-hand side of the road instead of the right-hand side of the road, you have to kind of figure out how to do things opposite that you normally do. Okay, I wasn't meaning to get a piece of scrap paper there. I've already got a table. So as far as the vertical asymptote is concerned, you can see that x is approaching 0. So we have a vertical line at x equals 0. And that's because if we had any argument other than less than 0, we can't evaluate the logarithm. So that's my vertical asymptote. X equals 0. Here we're getting 1/4, 1/8, 1/16. Those would be the values. Okay, so the first one is x equals 1/4. Y equals -7. 1, 2, 3, 4, 5, 6, 7. So 1/4, -7. 1/2, -4. So here's 1/2. 1, 2, 3, 4. 0. 1, -1. So we go over 1, down 1. Then we do 2, 2, 2, 2, like that, and 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So that's what it looks like. So you can see how we're stretching out the function in the y direction. I guess you could do 8, and log to base 2 of 8 is 3. And then if we took 3 times 3 is 9 minus 1, you're going to get 8. You can see how there's 3 units between each one of these. So the next one would be 8, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that would be the next point, like that. And again, the parent function in this case would be log base 2 of x. And that would look like this. So the log of 0 is, log of 1 is 0. Then the log of 1/2 is -1. Log of 1/4 is -2. The log of 2 is 1. And the log of 4 is 2. So this is your parent function. So what's happened is it's stretched. It's being stretched in the y direction from this 3, and it's shifted vertically down 1 unit. So you can see how this point is offset from that point by 1 unit. Okay, so those are sketching logarithmic functions. And let's see what else I got here. Okay, so we got one word problem. And this is, the model says that t is the time of the, it takes to pay off a mortgage. So t equals 12.542, the natural log of x divided by x minus 1,000. And x has to be greater than 1,000. Well, x is 150,000, so it's way above that. It says in the model, y is the length of the mortgage in years, actually t, I guess. So that should be t. And x is the monthly payment in dollars. Okay, so x is not this. And this particular model applies to these two requirements, $150,000 at 8% interest. And what you find out is the larger the monthly payment, the smaller the time it takes to pay it off. And this is if you plot it as a function of time. So this would be time on the x-axis. Actually, this is the x-axis is the payment, and the y-axis is the time. So if you wanted to pay this off in if you paid $2,000 a month, you'd pay it off in 8 years. If you wanted to pay $1,000 a month, you'd pay it off in 20-some years. So that's just using the graph. So what does it say? Use the model to approximate the length of a $150,000 mortgage at 8% when the monthly payment is $1,100.65 and when the month payment is $1,254.68. So you could try to use this graph. The problem is that, you know, here we're using it to like 6 decimal points, so that's probably not the best thing to do. You know, we could, I guess, we could draw, if we drew a vertical line here, let's see what happens. So here's 1,000, so 1,100 would be about there, and you draw a vertical line, and it intersects the curve about here. So that looks like about 20 years. And if you do 1,254, yeah, see, it's really hard to do that using the graph. Let's see. So let's look at this model instead. So I think all you have to do is plug in the number and evaluate the quantity. So it's really not a big deal. So it's actually easier just to plug it into the equation. So we'd have the natural log. So what we're looking at, I've already forgotten what the problem says, $1,100.65. So we'd have $1,100.65 divided by 1,100.65 minus 1,000. So this would just have to use our calculator that has a natural log function. So I'm just going to say 12.542 times the natural log of 1,100.65 divided by 1,165 minus 1,000. Close parentheses twice, and I get 30. So put that in your calculator, you get 30, which is 30 years. Now the second one is for higher payments, so you'd expect that to reduce the time required to pay it off. It's probably going to be 20 years. I'm just guessing, but so we'd have the natural log of 12. What was the number? 1254.68. 1254.68 divided by 1254.68 minus 1,000. So I plug that in our calculator. Well, actually, I can just reuse it in this particular kind of calculator. So I'm going to have 1254.68 and do that again. 1254.68, push the enter button, and I get 20 years. So you can see I pay another $150 a month, but I pay the mortgage off in 2/3 of the time. So that's why it's always good to try to pay as much as you can off on your mortgage. Ultimately, you're going to save a lot of money on interest, especially in this case because it's 8% interest, which is pretty high. Okay, approximate the total amount paid over the term of the mortgage with a monthly payment of $1,165 and $1,254. So all we have to do there is just take, so this is part B, we have to take the length of the loan, 30 years, times the number of payments per year, 12 months per year, and then we paid $1,165. This difference is going to show how much less money we have to pay if we have a 20-year mortgage instead of a 30-year mortgage. So we pay $396,234. So for the $150,000 mortgage, we pay $396,000. Now if we had 20 years, do the same thing. We just change the number of payments, total payments, which is the number of years times payments per year, and then multiply by the higher payment. But because the number of payments goes down considerably, this number should be smaller. 20, well, not should be, will be. So we get $301,123. So by paying it off in 20 years instead of 30 years, we're saving $95,000 approximately. And so the third part is asking for the interest. So the interest is just the amount that we pay beyond the actual price. So for part A, for the 30-year case, the interest is going to be equal to $396,234 minus the amount of the mortgage, which was $150,000. So if we take $396,234 minus $150,000, we get $246,234. And for the 20-year mortgage, the interest is going to be $301,123 minus $150,000. So 301,123 minus 150,000, and we have $151,123. So you can see how much less we pay, about 90,000, something less in interest. So that's it. That's just to kind of show you a practical example where logarithms are used. In this case, we're modeling the amount of payment, how long a mortgage would be for a given monthly payment.